multivariable functions can be very visually pleasing, as opposed to singular variable equations, as they can be graphed on the two-dimensional plane. One type of multivariable function you're likely already familiar with, albeit not very exciting, are linear functions. Linear functions get their name from the fact that both variables have degree 1, meaning that the change of x will stay consistent throughout the entire function, and so will y. Now, let's say you wanted to find all of the rational points on a linear function. In other words, how many points on the graph have both an x and y value that can be represented by the fraction of two whole numbers? Take the function y equals negative 2x plus 4, for instance. We can clearly see that the function passes through the point 2, 0. Because our slope, negative 2, is also rational, this means that we can change the x and y values from 2, 0 by rational numbers. And if you change a rational number by a rational number, as you might expect, you get another rational number. Therefore, assuming a given linear function has at least one rational point and has a rational slope, it will have infinite rational points. Now, let's consider the graph of a circle. Let's take two random points on the circle. We'll call P1 and P2. Now, let's draw a straight line through these 2 points, the slope of which we'll call m. If we assume P1 and P2 are both rational points, then we can infer that the slope of m connecting them must also be rational. This is because the differences between the x and y values of two rational points must be rational. Similarly, the opposite is also true. If we are given one point on the circle to be rational, as well as a line passing through this point, the slope of which is rational, this must mean that the second point it intersects is, you guessed it, rational. So, how would one go about finding all of the rational points on a circle? First, let's try to see if we can find a better connection between the slope of a line and the points at which it intersects the circle. This will, of course, change based on what circle equation we are using, but for our purposes, let's stick to x squared plus y squared equals 1, the unit circle. To find all of the rational points, we can start by choosing any random rational point on the circle, since it will be connecting with every other rational point anyway. For simplicity's sake, let's choose 1, 0. Using the formula y equals m times x minus h plus k, we can represent the line that passes through this point with the equation y is equal to m times x minus 1. To find the points of intersection, we now simply have to plug this equation into our circle equation of x squared plus y squared equals 1. Now, after some rearranging, we can see that these systems of equations can be turned into a quadratic. After finding the solutions to this quadratic, we get x equals 1, which makes sense since we started at 1, 0. But we also get another solution, shown in the image, describing the next point of intersection. These solutions can be used to find the points of intersection for any given rational slope m. We've just proven that all pairs of rational points along the unit circle are connected with exactly one line that has a rational slope. Therefore, this actually also proves that, similar to linear functions, when a circle passes through at least one rational point, that same circle will have infinitely many rational points, given that there are infinitely many rational slopes. As you might expect, this is actually true for all circles with varying center points and radii. Just as long as you have one rational point to start with, you will always have infinitely many rational points. As it turns out, this is not only a property of circles, but also of quadratic functions. The reason for this is simple. Drawing a line through a rational point will still create two intersection points. Therefore, there's still a one-to-one correspondence with the line of a rational slope m and a pair of points on the quadratic.